DST worth rupees 3 crore and has been granted 6 patents. He is currently working on quantum computing, blockchain technologies, wireless sensor network, machine learning for VLS, low power DSP architecture. Dr. Ravindra holds 120 publications in reputed journals and conferences. 3 scholars have been awarded PhD during his guidance, and 4 others are pursuing it. He is associated with some of the prestigious bodies like IEEE Senior Member, ACM USA, Fellow IET and IE. Above all, Dr. Ravindra is a passionate teacher. Now I request Dr. Ravindra sir to take over the session, please.
Design, but without giving the fundamentals of some basic DSP, it's not good to start the design and other issues. Okay. Probably I may ask some couple of questions because these questions are well required to understand the realizations. Okay. Let's begin with this. Suppose you have let's take this particular transfer function. Forget about whether it is IR filter or FAR filter or any other filter. So if you look at this digital filter, there is a difference between the digital versus the analog, where you normally represent this as H of S, which is normally S by S 1 by S minus 2, because this is the general format of a analog filter, and this is the general format of a digital filter. Why you have Z in the numerator, once we understand the linear phase concepts, then probably you will understand here Z by Z minus 2, and the standard approach here is 1 by S minus 2. It cannot be S by S minus 2. Okay, so there is some kind of misinterpretations between analog and digital, that you can replace S with Z, but normally that's not correct. You cannot replace S with Z because there are some kind of the transformation techniques that we need to follow. So if you look at this kind of design, you can clearly understand that here you have the pole at Z equals to 2. Now you have to normally decide the region of convergence. So if I assume that this is a causal filter, then in that case it's going to be a mod Z greater than 2. So in that case, if you would like to plot the ROC, then it is above or outside the outside 2. That's what this equation talks about, because you're talking about the causal. The causal filter is nothing but the whose impulse response starts from n equal to 0, right? So normally it is outside the outermost pole. So you have outermost pole, because I have only one pole, so therefore I would say that outermost pole is nothing but 2 outside. So therefore, when I consider this from 2 to infinity, clearly you can understand that you are not covering 1. So therefore there is no unit circle here. So therefore you can say that this is mostly unstable system, right? So Z by Z minus 2 happens to be an unstable system, but whereas if you look at this Z by Z minus 1 by 2, assuming that this is causal, so you have Z greater than 1 by 2, wherein that covers 1, so therefore that you cannot say. So therefore this equation you can also write it as something like this, right? Both are same. So therefore the upper bound I can write it as infinity. So between 1 by 2 and infinity, you can cover 1. So therefore that's a that covers unit circle. So therefore that is a stable system. So why actually we are talking about we are talking on this? There's a reason behind these points, because when you start realizing this kind of the filters, there is a way of implementing them. So therefore, whenever there are 2 things, or I would say 3 things, normally we float in the engineering or as well as in the technical courses. One, normally we call it as analysis. Okay. The second one you call it as design. The third one you call it as synthesis. So most of us heard about these names, right? So what is analysis and what is design and what is synthesis? So can anybody say what is analysis? For some time just forget about I mean do I have freedom to ask the questions? Yes, thank you, right, okay. So you're all my students for at least 2 hours, right? So let me ask some questions. So what do you mean by analysis? How do you define analysis?
Trying to know the objective.
Okay. Design?
Creation, prototype.
Creation of prototype. Synthesis?
Simulation.
Implementation.
Whether the analysis has been achieved or not. I think
Let us convert all these statements into the technical
Gate logic.
gate logic.
Yes.
Okay. Let me put in this way. So I have a system this way, right? So this is input and this is the system and this is the output. How normally you define analysis is that given the input and system, calculating the output. Network analysis, because that's what normally we call it as a course called. It's not network design. Engineering circuit analysis, electronic circuit analysis. Whenever you have the word called analysis, you must clearly understand that, right, I have an input there and I have a system. System is properly given. It could be a bistable multivibrator or whatever it is. And there is a proper input and I will calculate the output. So if you give this kind of the questions in the class, answer must be unique because everybody will get the same output, assuming that everybody has done correctly. But on the flip side, design is slightly different. That's the reason you call it as a digital logic design. It's not digital logic analysis. So system design is one step ahead of analysis, wherein there is a challenge here. That means I'll give input, I'll give output, you need to tell me the system. So this is what you call design, and wherein in this case the answer is not unique. Because let me take this way, I'll just give you one more example. So I have A, B as the inputs of a kind of a gate, some gate. I'm not talking about what gate is that. And these are the combinations I have taken, 1, 0 and 1, 1. And let us say that I have taken some kind of the output. Now as soon as you say this, immediately I can say that it is NAND gate, true. NAND, right? Yeah. So therefore, this is the one. But we are all aware that this is not only the way of designing the same thing. There are multiple ways. So therefore, I have given the input, I have given the output. Now when I ask you to get me the system, there are multiple ways that I can design this. So therefore, design is not unique. So that's what you need to understand, that IAR design, it's not analysis. So therefore, whatever the topic that I'm going to cover is not the unique way to design that particular one. There are multiple ways, right? So therefore, whether it is a FIR design or IR design, so simply we call it as a filter design. So therefore, filter again a kind of a system. It filters something, whatever it is. So it has got some kind of the characteristics, and based on those characteristics, you just have to design that. But the last one is much more difficult than the design, which normally use this term in the in VLSI, right? So wherein I'll give the output, I'll give the system, you need to tell me the input. So this is the extreme case, wherein let's say that you have a vendor wherein they'll say that you have to get me some kind of the input where my chip will give me 0.3 watts of power, as well as the delay is something like that, maybe 200 nanoseconds or 300 nanoseconds. So therefore they fix the system, they fix the the output, and you need to understand the input there. So therefore there is a lot of difference among all these things. So whenever you are using the word design, we must clearly understand that the process that we are going to build here is not unique. There are multiple ways. Why I'm saying this point before I put the heading in the sense, I'm going to design, or I'm going to explain 4 techniques here, like Butterworth, Chebyshev. These are the 2 techniques that we discuss, but as far as my knowledge goes, there are almost more than 50 techniques to design a filter, right, with the characteristics. So that's the first point. So all right, so this is the next point that we need to understand. So, and why I said the first point, the stability, is also an important thing, because we assume that whatever the characteristics that we build, we assume that they produce stable system. That means whenever I say design, so therefore the point is the system must be stable. You cannot really talk on unstable system. Designing of unstable systems or marginally stable systems are not the interest of this particular one. Okay, so that's keeping that point in mind. So let us understand this. Okay. So how do we begin this point? So whenever you would like to design this, I'll tell you what exactly infinite impulse response, that we'll understand that later. But before that, obviously it is going to be a filter. Okay, so therefore it's going to filter certain points. Normally unwanted components it is going to think. So as far as our knowledge goes, we have LPF and we have HPF and BPF as well as BSF, and we have something called all-pass filter. We don't really discuss that because that's an ideal filter, right? And among these four, let us restrict this particular topic to these four. So though I am given 1.5 hours or 2 hours to finish off this, trust me, this topic will take 25 hours. So it is a bit vast. So now, what is this LPF low pass filter? Ideally, how do you plot this? Something like this. This is how you are going to plot this. If I ask you to plot the frequency response of the low pass filter. So obviously there are certain things that we have to always understand. That means pass band as well as stop band, right? So therefore this band of frequencies, normally this is what you call it as a cutoff frequency, which separates pass and stop fundamentals, right? So this is the pass band range, bandwidth, and this is the stop band. So having known this low pass filter, you can always design the high pass filter. It's very easy. So how do you do it? So it is all pass filter. What is all pass filter? It allows all frequencies. Mathematically I'm trying to explain, but when it comes to design perspective, it is slightly different. Okay, all pass filter minus this is going to be a high pass filter. That means when I subtract this, then what kind of component that you get? You get something this way. So therefore this is going to be stop band ideal low pass filter. This is ideal low pass filter, but there's no point in talking ideal low pass filter because you cannot have the sharp cutoff frequency. That means that let us say this is 50 hertz, 49 it passes and 51 it stops. So such kind of frequencies you will never get it. So the other point is we'll be designing what? Low pass filter. So that is the next point. So therefore now we have seen, so before I go ahead, so I'm just giving the fundamentals. So the first one we discussed the stability, right? So therefore we are going to talk on only stable systems. Okay, unstable systems are not our interest, though we can do it. And the second point what we have discussed is the design, the concept of the design. And third point is why we have chosen low pass filter in the process. So these are the 3 points which gives us the fundamental. So next time whenever we write low pass filter, we should never get a doubt that why we are doing the low pass filter, why not high pass or band pass or band stop, because if I know that, the rest of the things are automatically passed. Now when I considered the low pass filter, so just now we have drawn the ideal characteristics, but let us understand the practical characteristics here. So it is something this way. Okay, so this is the magnitude response of a filter. Okay, actually this is also not correct, frankly speaking, right? Because still there is a problem in this, because the magnitude cannot be straight line what actually you see in electronic circuit analysis. So normally you give these graphs in the similar graph papers, you will ask them to write, but when it takes the filter perspective, this is also not correct, but let us understand this because there are a couple of points that we have to see. And let's say that this is the maximum magnitude. Okay, so normally we draw a line here, and let us say that this is A or AV or AI, whatever it is, and you call this as a 0.707 AV, very standard numbers, right? Why is that? Why is 0.707? Why? Why 1 by root 2? 1 by root 2, if you understand 3 dB, you will automatically understand, because log 1 by root 2 is nothing but -3. Why 1 by root 2?
The frequency will be equal to
How?
FYFC, 1 by root over 1 plus FYFC.
That is formula, that is okay, but my question is why 1 by root 2? Why can't be 1 by 2 or 1 by 3 or 1 by...
Considering FC to be unit.
Why?
Square root of gain expression will be that's 1 plus gain into 1 by root 2 times of 1 minus f by f both of them are like that. So 90 is
Power drops by 50%. Power drops 50%.
True. Why 50%? You are close to my answer. Very close to the answer. Why 50%? There is a theorem associated to that. That is where we have to start. It is maximum power transfer theorem. If you wanted to get the maximum from the source, you have to apply the maximum power transfer theorem, where P equals to I would say V into I. Therefore, whenever you are calculating the power gain, it is AV into AI, and this supposed to be 2. Here also it is 2, assuming that voltage and current are interchangeable. So therefore it is AV by root 2 or AI by root 2. Then this root 2 you have to write it here. So therefore whenever I write 0.707 AV, that means that I am expecting the maximum power from the system. But it can be 0.8 also. It can be 0.9 also, it can be 0.95 also, or it can be 0.99 also. But other than this particular one, if I write anything, that means that my system is not in a mood to give maximum power. So we need to understand that first, otherwise every time we'll write 0.707 AV only. When you write every time 0.707, that means every time you design the same filter. Is it not? So therefore, that means then what are the meaning of the specifications that I am going to write down here? That means that everybody in this world is expecting only one type of the filter, which is not good to think. So therefore, this particular 707 can be varied. It can be 0.8 or 0.95 or 99. It is my wish. Right. And I am going to draw one more line here. So this is 0.1 AV. Why again here 0.1 AV? Rise time versus fall time, because the 10% of, you have to allow minimum 10% of the time to reach or to respond the system. So that means above this the system is start getting respond. So therefore this particular one will cut the magnitude response at some point, and you have to drop down that, and this is what you call the passband frequency, and this is what you call the stop band frequency. Now this is my passband, and this is the transition band, and this is the stop band. So this is the ideal way of drawing the low pass filter characteristics, but not exactly, because I'm going to draw one more graph now. So that's where you can expect the more practical things, right? So now so in this particular graph, what all the things that are required? So if you look at it, there are 4 things here. So you need to understand that how we are designing the system, right? So therefore whenever you are considering any particular project, normally it is expected that what are the parameters or what are the design values or design constraints that you are looking at here. So the first one is I am going to give you passband gain, which is nothing but this value, and I am going to give the passband frequency, and I am going to give you stop band gain, that means that this particular value, and omega s. So these are the 4 values will be given. From these 4 values to till either FPGA implementation or ASIC implementation we have to take. So that's what actually we are now going to do it. Okay, right. So now what is the first point? What are our inputs? These are the inputs, right? And the outcome is you need to design. You are expected to do a IR design, wherein let us see how best that we can do it. But that is one way of understanding it. But there is a second way of look at the same point there. So in this particular band, you have a point here like this, and this cannot be a line, but it is something like a, yes, you may get like this. Okay, so therefore it's not a line now. So you may have some kind of the ripples. That is the reason it is called 1 minus del p and 1 minus 1 plus del p. So in that band the signal will oscillate, and this you have to connect to the Gibbs phenomena. So what is the Gibbs phenomena? Gibbs phenomena is something like this. So what he has done is that this is a square waveform and this is a sinusoidal waveform. So can I say that the square waveform is equal to sinusoidal waveform? No. Why not? I will say yes. I will say yes, because you need to, yes, you need to always calculate the error between the square waveform and the sinusoidal waveform. And if you consider this particular one, the error will be some 20 to 25%. So if your system allows 25% of error, then you can replace the square waveform with a sinusoidal waveform. You have to ask a question to yourself, can I allow this much of error? Yes, no. If it is no, then you have to take the second waveform, that's nothing but the orthogonal or harmonics. In that case, you get like this. This is only sine theta or sine t, right? But if you add sine t plus sine 2t, there are 2 harmonics here. That is the reason you get 2 peaks here. 2 peaks in the sense 2 harmonics. 1 peak in the sense 1 harmonic. So that's how you have to draw the sinusoidal waveform. So therefore it comes like this and it is. So if you go like this, then definitely the error will be reduced, minimized compared to this. Now here error may be 15%. Again you need to ask a question yourself, can I allow 15% error? Yes, no. Yes in the sense you can replace, otherwise no. No in the sense again you have to go for 3 harmonics or n harmonics. That's what actually Gibbs proposed long time back, and that we call it as a Gibbs phenomenon. And you need to observe that point here. Here I have taken 3 harmonics. Okay, those harmonics are now called as ripples. So this is how the practical low pass filter, the magnitude response, right? So now when I compare these two, either we can design this or we can design this. So when I have the design constraints, okay, so I have 2 ways to do it. Okay, right, and this is Chebyshev design. Okay, so what do you get at the end of this? You get HA of S. That means you get analog transfer function. So that's what I said, because you are designing it, and we have chosen only 2. But as far as my knowledge goes, there are almost all 50 techniques that are available here from the constraints, from the design constraint to get this HA of S, and we are discussing the most easiest techniques in the design of this the transfer function. So now you need to stop here and then move to control systems, okay, and then apply all these stability techniques and verify whether this system is stable or unstable. If it is unstable, then you have to stop here, go back, change the design constraints, again apply these two techniques and then come. It has to go like this. Okay, you should not proceed further, because if you miss here, then again you get somewhere h of z after 4 or 5 steps, and there you have to apply the stability techniques in the digital transformation, where they are the toughest techniques compared to this, whereas here you have the most easiest techniques in the control systems. Now once you have this HA of S, here again you have two techniques here. No, actually this is HA of S LPF. Okay, but let us say that the design the design technique is HA of S, you want to design HPF there. Okay, let us say that is a task, or BSF or BPF, okay, any one of them. Then what you have to do is you can apply the transformation here itself. That means from low pass to high pass or band stop, here you can apply, and you can get the desired filter, and from then you can proceed. That is one way of doing it. But the other way of doing it is converting this particular one at the last. Now here also we have got two techniques. So this is bilinear transformation technique and impulse invariant technique. Okay. So that means from constraints 2, and what is the output here? Here the output is you get h of z. Okay, and h of z low pass filter you get, and the task is, let us say, high pass filter. Now you can convert this digital low pass filter to digital high pass or digital band pass or digital band stop. Either you can convert the filter to filter techniques, or you can also convert the filter to filter techniques. So this is h of z. Once you get this h of z, then yes, you have to realize this. So realization, again, direct form 1 you have, as well as the direct form 2 you have. Okay, right, direct form 2 you have. Once you have the realization, then you get the coefficients. So based on the coefficients, you can write an FPGA program to implement this, or else you can write a Verilog code for this and then take it to ASIC design. So this is the software to hardware flow chart. Okay. Right. So this is the entire flow. Now let us now here, if you look at it, either Butterworth bilinear or Butterworth impulse invariant, Chebyshev bilinear and Chebyshev impulse invariant. So therefore here we can design this into the four ways we can design this. And between Butterworth and Chebyshev is the better than Butterworth, because you get more ripples, right? Because if you have more ripples, that is the the nice flat you get, approximation or nice flat you get it. So Butterworth will have the more number of ripples, Chebyshev will have the more number of ripples, so therefore Chebyshev is good. And compared to bilinear versus the impulse invariant technique is better than the bilinear. Okay, because in this particular case you are going to do 2 approximations, so that's the another disadvantage there. So Chebyshev versus the impulse invariant, and this is not that suitable. So this is the actually the fundamental that we have to now look into. Now let us understand the Butterworth design, okay, and then how do we go for it, and then Chebyshev design. Okay. Second and third like this. First. Next. This part already discussed. Next slide. Yeah. So this is also discussed. So this is actually the pass band. You have got only 2 ripples out there, and here also you have got the 2 ripples, and that's what we are trying to do. So therefore, this is the what do you say? The practical low pass filter, magnitude response. Right. So you just look at these numbers. So there are certain things. You would see that the capital omega as well as the small omega components. Something this way. Here you have the pass band H frequency in radian per second, and the small omega p is the pass band in the H frequency in radian per sample. So you need to look at the four components. There is a capital omega p, omega s, and small omega p and small omega s. And the conversion between them is omega p equals to omega p by the sampling period. Next slide, please. Right. Now let us go to the Butterworth design, and here you look at the magnitude response h j omega whole square. That means magnitude response equals to 1 by 1 plus omega by omega c whole power 2. So this is the one that he has predicted in this process, and he has given that particular magnitude response. But now there are number of questions that how best is that particular equation? Is it correct or wrong, or what is the approximation and all of things? Okay. But if you look at the particular equation, if you try to expand 1 plus x whole power whole square, you look at this equation. So it is 1 plus x whole square because n is another number, and the left side you have a square. So therefore, if you take even the other side, you get the square root. So how many expanded forms that you get? Silence, please. Those small voice is discussing myself. If you have any questions, please stop. Then you have those equations, the 1 plus omega by omega c whole square. And if you look at that particular equation, based on that, it's an approximated curve. So therefore, some estimation techniques are being used to get that particular equation. And if you plot that equation, it is more or like looking like a low-pass filter frequency response. So based on that, he has done the curve fitting, and he finalized the Butterworth magnitude response is something like that. So this is what actually we have to first understand, that there is no fundamental proof for that particular equation. Okay? So based on that equation, so whenever you try to plot this, then you get this kind of equation. Or it could be the other way around. So how he has done, nobody knows. He might have drawn these waveforms and then applied the curve fitting equations, and he might have got this particular equation, or he predicted something and then he got it. So but some other way, for that particular equation we are getting this. And if you look at that particular equation, there are less number of ripples in the magnitude in the pass band. But if you look at the Chebyshev, whereas the entire equation is expressed in terms of hyperbolic functions of cos, wherein you get more number of ripples in the same pass band. So that's the reason, more, that's what we thought, that Chebyshev is better than Butterworth. Right. So this is a small fundamental thing, that how we have to design the poles. Okay. So just have to expand that, and I'm assuming that s equal to j omega, and this, look at that equation, 1 by, do you have a mouse? So 1 plus s by j whole power 2n equal to 0. So rewriting that, you get several poles on the unit circle. Right. So based on those equations, that we can design this. Yes. Now the point is, what for that equation is given? That is 1 by 1 plus omega by omega c whole power. So omega c will be given to you. That means the cutoff frequency will be there with us, right? And omega is also there. So for various frequencies, by putting the omega c value, you can always calculate the order of the filter. So this is what actually he has done. So for n equal to 1, so if you substitute that, so you have one pole here. So this is the another point that we have to always understand, that the poles will always come with their conjugates. So therefore, this is normally I'm talking about a jet plane, but if you look at the S plane also, if you have a complex pole here, 2 plus j, something like that. So obviously we also have, this cannot be 2 plus j, this will be minus 2 plus j, and this point should be minus 2, minus 2. So they always come with their conjugate. So that means if you have one pole here, let us say this is unit circuit,
That means this is 1 angle 0. Its replica is going to be 1 angle pi. Okay. So now you simplify this. This is r angle theta, right? This is r angle pi. So therefore, there must be so therefore this is pi by 2. Then this is going to be 1 angle minus pi by 2. And it can also be 3 pi by 2 because this is 0. Pi by 2 pi 3 pi by 2. It can also be minus pi by 2 if you get from this side. So therefore, you see always them with respect to their ripple. So therefore, if you have n equal to 1, then he has designed what kind of transfer function that you get. So that's what I said in the beginning. So you have the 4 parameters omega p, omega s, and ap and as. So these 4 parameters. From these 4 parameters, if you choose the butterworth and if you get n equal to 1, straight away we can write the transfer function as 1 by s plus 1. So similarly, you take n equal to 2 and n equal to 2 in the sense you need to look at the k values there. So k equal to 0, 1, 2, 3. 3 values you get it. So therefore 4 poles and those are the 4 poles are located there, pi by 4 and then followed by move pi by 2 again because j turnover. So pi by 4 plus pi by 2 plus pi. So therefore you see that those corners diagonals if you combine it. So pi by 4, this is 5 pi by 4, this is 3 pi by 4 and this corner goes to be 7 pi by 4 which is nothing but again minus pi by 4. So based on that if you look at it, so for n equal to 2 you get it as 1 by s square plus root 2 s plus 1. So that is the reason for n equal to 1, n equal to 2, n equal to 3 we normally ask, so for n equal to 1 if you get it, directly we write down that as 1 by s plus 1. N equal to 2, we will write down the same. N equal to 3, it's going to be 1 by s plus 1 into s square plus s plus 1 and n equal to 4, you get another equation, n equal to 5, 6, 7, n equal to 1, okay, n equal to 1, 2 if you look at it. So here, this is the transfer function directly that you are building it, right? So, order 3 in the sense, we've got here 3 poles, right? Because this is 1 pole and this is 2 complex poles. N equal to 4 also we have. So beyond n equal to 4, it's hard to remember. N equal to 4, 5, 6 and other count. And if you consider n equal to 4 here, then what will happen to digital filters? So you get z power 4. Because, so here you have this s cube, right? So this is going to be 1 by s cube and so on. So 1 by s cube, if you apply the bilinear transformation technique or impulse invariant technique, then you get this as 1 by z cube and so on. Okay. So realization of such filters is going to be made. So for a pen and paper concept, so mostly the n value is fixed at 3 ideally. Okay, you cannot go beyond that. Makes sense. Yeah, so this is for n equal to 3. So we have given a generalized response, n equal to 4 and n equal to 5, and that will be the denominator. So n equal to 4 in the sense s square plus 0.765 s plus 1, and that is 1.84, that was 166. So that much you have to remember, and you need to program that also. It's not that by just designing the numbers, and you need to look at them in terms of MATLAB. MATLAB simplification is easy, but when it goes to Verilog programming or FPGA programming, it is going to become the toughest job. Okay, so that's what normally we say in the industry, that designing of digital filters is very easy, but when it comes to analog design, most of the time we copy it, and that is allowed. That is allowed in industries. Yes. So now let us understand the same concept with the ripples model. So now what actually we have seen from the now again we are going back to the specifications. Now we understood the Butterworth design, right? So we have taken the equation, and how we have taken that equation also explained based on the computing or maybe a guessing part of thing. We don't know how he has done. In 1930, he is a Russian scientist, Russian engineer. 1930s and 40s he developed that equation. And this is the ideal one that actually we studied. But there we have written 0.707 AV and 0.1 AV, but he is writing in terms of the ripples, right? Kp as well as the Ks, which is nothing but 1 minus delta P versus 1 plus delta in that range. So now Kp is the attenuation at passband frequency. That's the reason, because you are talking, it is an attenuation, so therefore you get in terms of the negative values. Okay, whereas Ks is the attenuation at the stop band frequency omegas. And look at those values. It is Kp less than or equal to 20 log h omega less than or equal to 0. That 0 is correct, which you have it on the y-axis, because you are talking about the attenuation. So 0 attenuation in the sense it is a maximum allowable frequencies. So here these are the equations that actually I have derived. Of course, all these things are available in the open book. And this is the Kp value. Okay, and passband frequency will be there, and this is the cutoff frequency whole power 2n. So n we have to calculate first of all to do this. So from the fundamentals, we need to calculate the n value. That n value we have to substitute here, and then you get this Kp. And similarly the Ks value. And that is the n value if you look at that. So log 10 power minus Kp by 10. Kp is negative, so therefore it is meaningful. So minus 1 divided by. So based on that equation, we have to calculate this. Actually, this is not correct. If you look at this, you take cutoff frequency with respect to the pass band. You take the cutoff frequency with respect to stop band. You get different values here. Though we have written this R, but always the cutoff frequency should belong to pass band. It should not belong to the stop band. Okay. So there will be 10 to 15% error exists. So we have to be careful while you do that. Then you can ask me, then why I have taken that? So when we say that it is wrong, then why we have chosen this? Why we have chosen this in the sense there are some times that you will have more ripples. So you have 2 ripples at in pass band, and here you have more ripples in stop band. When you have more ripples in stop band, it is better to choose stop band. It's this one. It's better to choose this. So when both are same, then we have to transform that S turns to S by omega c. That we have to do it because analog low pass to low pass frequency transformation. That means Butterworth design is meant for the analog low pass, but for this particular filter we have to do it. Because if you look at the equation, the n that we got it, so in that particular derivation we haven't used any one of them. So therefore, again the transformation should be done, which is S turns to S by omega c. So this is one problem that I would like to take up here. Okay. Then I will directly go to the transmission because there are some 10 problems I have calculated. Right. So let's say that that's the equation that we got, the same equation that we have seen. So if you have seen the 0.707, that means that you are expecting a maximum power transformation, which is the maximum band is 1 between 0 to 0.3, and whereas this side is supposed to be 0, the 0 is not filtered. So 0 equal to mod h of omega less than 0.2, which is nothing but 0.752. And look at these values. Just have to look at this because the omega p is not given directly, but you need to calculate the omega p and omega p. That's what that we have chosen here. And the passband frequency, you can look at it because it is 0 to 0.3 pi. So that is the passband frequency. From that, we have to calculate the edge frequency. Okay. So to convert that into the Butterworth transformation, which is nothing but omega p by t. But here the sampling period is 1. He has given the t equal to 1. So therefore, capital omega p equal to small omega p by 1, which is nothing but 0.3 pi. And similarly, the stop band frequency also 0.75. So therefore, that we have converted here. by applying the pi value. So you get this omega p as well as omega s. And here ks and kp also we have calculated using this particular one. So kp equal to 20 log 0.707, that means lowest value, and ks is nothing but the lowest value, here also 0.2 this side. So by substituting all these values, you got n equal to 1.73. You need to always seed the value to the upper point, so therefore you get n equal to 2. So this is 0.2 that you got, right? So here there are two procedures. You don't look at this side, right? This side is already explained, this part. But you look at this one. This is because n equal to 2 you got it. So directly you can choose this value. hs equal to 1 by s square root 2s plus 1. Because for n equal to 1, what is the transfer function? N equal to 2, what is the transfer function? 3, what is the transfer function that we already calculated in 5. So, I mean, you don't need to have that. You don't need to have that, but still you can apply this particular equation and get this. If n equal to even, this is the equation that you can apply, but you will land on the same value. Or else, understand n equal to 2 and applying the 4 poles, but if you simplify this, you get the same value. So therefore, either this procedure or direct value, anything is fits correctly. So now you can apply this. So from then, that's what the Butterworth said, for n equal to 2, 1 by s square plus root 2s plus 1. But where are we using our values? Right? So that means that whether, see, you look at this equation. Just understand this point. This is the critical. That means why I am transforming like this. S turns to s by omega c. That's we need to understand. So look at this particular data. 1.7336 approximately equal to 2. You have chosen this transfer function. Suppose if you get 1.85, that is also approximately 2. Again you choose the same transfer function. Suppose if you get 1.1, again you choose the same transfer function. So therefore, irrespective of any of those values which you have taken in the magnitude response, you are getting the same value. So which is not correct design. So that's the reason we have to transform to the original characteristic. So therefore, s turns to s by omega c. This omega c calculation, if you look at it. So what is the omega c? This is omega c, wherein ks you are using it. What is this ks? It is there in the design constraints. And this n. So all these values that you are using it, and that you are substituting here. So therefore, you get this transfer function. So this transfer function is the appropriate transfer function for the values that you have chosen. Otherwise, irrespective of the graph, you will land on only 1 by s square plus root 2s plus 1, which is not correct. So that's the reason this transformation is right. Now you have to stop here, move to control systems, and look at all the poles, location of all the poles. If you feel that it is stable, then we have to move further. Right. So therefore, stability conditions should be checked thoroughly at this point. And this is one more problem wherein I have chosen n equal to 3, the same values, okay, or similar values. And this is the transfer function. Directly you can get it 1 by s plus 1, s square plus s plus 1, right? And omega c value you got 1.45, and again you transform that, so you got the other equation. So this is the other transfer function. And here also the ringalization does not exist for analog filters. Okay, right? So this is the I'll skip the problems. Okay, so there are many problems, many complex problems that I have chosen. Right. Now you look at this Chebyshev filter design, wherein he has approximated this better than the Butterworth. So where he has taken more number of ripples in the pass band as well as the stop band to get the appropriate equation, more appropriate equation, better than the Butterworth. So wherein, so he has given this n equal to odd, because you look at this, here you have the 3 points, and of course this is assumed to be the fourth one. So here also you have got the 4. So that for n equal to even you have like this, n equal to odd you have like this. So he has also calculated the error value, which is nothing but 1 by under root of 1 plus sigma square or epsilon square, whatever. So he has approximated this with the cos h inverse hyperbolic functions, which is better curve fitting than the square functions, which is nothing but 1 by 1 plus x square. That's what actually the Butterworth dash. So, but the equations are a little complex in this case. Okay. So for n equal to even, this is the equation. For n equal to odd, this is the equation. And where there are some unknown values here, bk and capital and small and ck. So those values are given. So we just have to calculate all these values and then get the point. But once you get this, the same transformation should be done. So this is one typical problem where I calculated this n equal to 3, and the calculations are a bit lengthy. That's what I said. You must have the calculator to do all these things. At least yn values and c0 and pk values. So you get this. Now you look at the coefficients. This is n equal to 3 part. But the same particular same problem I've done. The same problem I've done here n equal to 3, which is not that complex. Yeah. So for n equal to 3, this is n equal to 4, which is not that complex. It's the same problem. So if you look at the coefficients part, it's not the same part. But if you have the coefficients, then digital design is also be a tough job. So big complex. So you have the n equal to 4 also I try to do. You must have a lot of patience to do this. So this is the basically the Butterworth as well as the Chebyshev design. So again we'll go back to the point wherein you get this. So you get this. So with the constraints that what we have, that omega p, omega s, and ap and as. So what we get is you get h of s, analog transfer function, either using the Butterworth or Chebyshev. But as I said just now, the Chebyshev is better than the Butterworth we have because of the more number of things. Now once I have this, then I have the other point. Now should I use impulse invariant technique or should I use bilinear transformation technique to do this? So this is the next part that we have to choose. Now what is this impulse invariant technique? In this case, if you look at the bilinear transformation technique, normally, so how do you transfer this S? So what is the technique that you have to follow to transfer this particular S? So yes, so it is 2 by t, 1 minus z inverse by 1 plus z inverse. So this is how, wherever you have the s, you have to replace s with this particular number when it comes to bilinear. Whereas in the impulse invariant technique, so this is what actually again we need to look at this. So 1 by s plus 1, okay, versus 1 by, is it stable or unstable? Stable. 1 by s plus 1 whole square, also stable. Unstable. Unstable. But both the poles are on the left side of S plane. Stable. Stable. Then 1 by s plus 1 whole cube, also stable. Is it stable or unstable? My question is simple. 1 by s plus 1 stable. 1 by s plus 1 whole square? Stable. S plus 1 whole cube stable. Whole power 8. that is the once if you understand this, then you will appreciate inverse invariant technique. Why inverse invariant technique is better than bilinear transformation? I'll tell you. I just have to go to time domain, control systems. Then I'll come back to this. E power minus AT. Let us plot this graph. Most of us know this. So it is exponentially decreased. How about t into e power minus AT? We are talking about the Laplace transform. So I am talking about the graph. How is it becomes unbounded? No, it's not unbounded. If it is unbounded, then no. Positive number plus negative number. Negative. Positive. Zero. One big. Same concept you have to apply here. T is unbounded. E power minus AT u of t is bounded. That means you are multiplying one unbounded signal and one bounded signal. So therefore resultant is no. Depends, because t linearly increases, e power minus AT u of t exponentially decreases. By the time it reaches to infinity, e power minus AT u of t will bring it back to 0. That is the reason 0 to t it looks like unbounded, and beyond that it looks like bounded. So therefore this is t e power minus AT u of t graph. So it has a nature at one particular point, it has a nature of unboundedness. So this is how we need to understand t e power minus AT u of t in time domain, and 1 by 1 plus 1 by s plus 1 whole square. How do we understand this? This is stable, there is no doubt about it, but not better than s by 1 by s plus 1. Right? So that's where we call it as comparative stability. So compared to that, this is unstable. But if you look at me, I'm stable. So therefore, 1 by s plus 1 may be stable from, let us say, Sunday to Saturday. But 1 by s plus 1 whole square may be stable from Sunday to Friday. Its boundedness decreases. Suppose if you consider 1 by s plus whole power 8, you must say stable, but not better than 1 by s plus. So therefore the stability decreases. When you say stability decreases, it does not mean that it is unstable.
Maybe marginally stable.
Marginally stable. That's where I am going to bring. That is what you call
It actually unstable when it increases.
which one? Here, n. N when increases, we have this t power n there. So therefore, there's a lot of points that we have to understand. So why I said all these points to understand that you cannot transform S to Z with a single equation like this in bilinear transformation technique. That means 1 by s plus 1, 1 by s plus 1 whole square, 1 by s plus 3 whole square, or whatever it is, or 1 by s minus 1, which is unstable. So for every s, we are transforming this. I am not doing the derivation here, though it is easy. Okay, so s tends to 2 by t, 1 minus n. So therefore, the nature of s is not uniform. Right? Here it behaves different way, here it behaves in a different way, here it is something different. So therefore, it is getting changed. Because it is getting changed, therefore, s nature should also get changed. Now, what about this kind of repose? 1 by s square plus s plus 1. That means you have one pole here, you have one pole. Okay. So, are they stable? If I have a pole here and if I have a pole here. So now here there is another problem that may persist. Here They are not exponentially decaying like 1 by s plus 1, but they have this kind of dependency. Yes, oscillations. So the nature of this transfer function is different. That means the nature of this system is different. The nature of 1 by s plus 1 is different. The nature of 1 by s plus 1 whole square is different. When the natures of these systems are different, that means the behavior of s is different. When the behavior of s is different, how do you transform the same s into a single equation with this way? That means for every s you are replacing the same equation which is not supportive or which is not acceptable. So therefore, a linear transformation technique is easy. It's easy to derive, easy to substitute, easy to finalize your answer, and easy to realize. But there is a flaw in this, because all your systems will not behave the same. That's what it is. So therefore, we go with impulse inverting technique, wherein based on the transfer function we have. So if I have 1 by s plus p, then you must have 1 by e1 minus e power minus p into p z power minus. So therefore, depending on the pole, you transform the equation. If it is whole square, whole cube, then you have 1 by s plus p whole power m. If you have, then you know you need to use dt power or ds power m minus 1, you should write, and then use that. So therefore, for a different value, so how many types of systems that we may have? So I have a repeated poles, distinct repeated poles. Okay, so this is the case 1, and the case 2 is distinct repeated poles, and that means distinct poles, not repeated poles. Let us take distinct poles first, and then repeated poles, then complex poles, right? And complex repeated poles. So this is distinct poles, you can apply this. Repeated poles, you can apply this. And for the complex poles and complex repeated poles, it is given some big equations that we have to, I can show that we have to. Then finally, what you get? You get your H of. Okay. So here, once again, if you could not test the stability in the earlier case, at least you can stop here and then go for the stability. But digital stabilities are a little bit different, because you have to apply the Lyapunov stability, and there are the various other stability techniques that we have to do, which is most of the time which is complex compared to the stability techniques what actually do. Okay. Once you get this H object, then what do you get? Then how do you realize them? Direct form 1, direct form 2. So suppose you get this H of z, which is nothing but, let us say, z minus 1 by z plus 1, which is y of z divided by x of z. You cross multiply this, then what do you get? I am writing in terms of z, so it is not correct. It's supposed to be in terms of z power. Z inverse you have written, otherwise you cannot get the delay events. So h of z equal to, let's consider this, minus 2 z inverse, let us say plus 8 or whatever. So therefore it is something like y of z by x of z. So you multiply this x of z. While you are converting this, you can apply z power minus 2 in the sense. You get 2 delay events, y of z plus 2 z inverse y of z plus 3 y of z. Now you have to apply inverse z transform there. Then what do you get? You get it as x of n equal to y of n minus 2 plus 2 y of n minus 1 plus 3 y of n. Is it stable or unstable? By looking at this equation, how do you say whether it is stable or unstable? How to find out, by the way, stability?
Causal system.
How system, yes, can be causal but need not be stable. All causal systems are not stable. Right? So,
Then bounding condition we can apply.
in general, how do you find out this? In general. So, you have to find out the poles. Right? Once you find the poles, then the poles must be inside the unit circle. If all the poles are inside the unit circle, then you can say the system is stable. But actually, that procedure is not required. There is a simple procedure. So, what you need to do is y of n coefficient you look at it. So, the y of n coefficient you make it 1. If you wanted to make y of n coefficient 1, that means the whole equation you have to divide with 3. Right? So therefore, this is going to be 1 by 3, and here also 1 by 3, and this is 2 by 3, and this is 1 of n. The system can be set stable after making y of n coefficient 1, and if the remaining coefficients of y are less than 1, then the system is stable. That means this is 1 by 3, this is 2 by 3. That means this gives me one pole, this gives me another pole, and both the poles are inside unit circle. That is the reason we are saying that 1 by 3 and 2 by 3. Then why are we not considering this coefficient?
0.
Because x coefficients are zeros, y coefficients are zeros. That's the reason we always look at the y coefficients, not the x coefficients. So it can be 50, doesn't matter. Or it can be 100, doesn't matter. So this coefficient is gives me always zeros, and this coefficient will give me the poles. That's the simplest way to understand whether the system is stable or not. So then you have to go for the standard realization techniques that we have. This is the part that we have to always understand in taking DSP. Because first we always teach the realizations and then we teach the Butterworth and Chebyshev. There is a reason behind it. First, if you teach Butterworth and Chebyshev design, then you get the very complex equations. Now look at the equations that we got. So those complex equations, and if you convert them into h of z, designing such equations will become much more complex. That's the reason I am taking a so simple equation. And I can clearly explain the DF1 or DF2 technique. So therefore, what is the DF1? So what you need to do in DF1 is y of n on the left side. These are the simple techniques. Y of n on the left side and all other values on the right side. Right? So therefore, minus 1 by 3 x of n. Right? All is 1 by 3 x of n because these two will go this side, and minus 1 by 3 y of n minus 2 minus 2 by 3 y of n minus 2. So if you write this way, then the realization also will become very easy. So now forget about all these things. Okay, let's close this. Then read only this equation. So what is the equation? Y of n equal to 1 by 3 x of n. So therefore, what is x of n? This is x of n. Right. This is y of n. That's it. So if you write like this, then y of n equal to x of n. But what is this equation says? Y of n equal to 1 by 3 x of n. So you can simply write 1. You are done with the example. Now you need to add this. You need to add this. You need to add this to this particular part. Okay. So now this is y of n, right? So you get this y of n here and put a z inverse. Then what do you get here? You get here y of n minus 1 because you are delaying it by 1. But this is y of n minus 1, right? So this is y of n minus 1, but here you have a coefficient called 2 by minus 2 by. So it has to go back This is feedback. Output delays are always feedbacks. Okay? Because a part of output will be fed back to input. That's what you know. We by-hearted or whatever the part that normally we say part of output. So therefore, what is the part? Y of n. A part of what? Y of n minus 1. So therefore, that's the reason they always follow the reverse direction. So what is this? Minus 2 pi. And where shall we add this? If I add this, it's going to be x of n. But after that, again, you are multiplying with 1 by 2. So therefore, while you are drawing it, you need to rub several times. So therefore, this is 1 by 3x of n that you add it to. If you, there is a symbol here. If you put this way, this always represented as a multiplier. Okay? So here this is x of n, this is x2 of n. This is a simple notation in DSP, normally we follow this way. And what is the output means? You must say x of n into x2 of n. That's the notation. I didn't finish up that notation here. But whereas the same notation here, we put it, and here we put the arithmetic symbols here, some arithmetic symbols. In that case, you have to follow whatever the arithmetic symbols are there. If you don't put any arithmetic symbols, that means it's a multiplier. So small notation that we have to follow. So therefore, this minus you can give it to here, making this as plus, or you keep minus here, then you put plus here, and this is going to be this. And you can again read this. So minus 2 by 3 plus 1 by 3 x of n, which is equal to y of n. Correct. So this is. So next step. But here I have 1 by n minus 2. So you delay this one more time, then you get z inverse. So therefore this is y of n minus 2. That again you give it. And take this, again you need to rub this and then mark this. So this is going to be plus and this is going to be those. So here how much you got? That is minus 2 by 3 y of n minus 1 plus minus 1 by 3 y of n minus 2. That you are giving to this, and this is 1 by 3. So what are the elements that you have used? One delay element, one adder, one multiplier also is there. Because y of n minus 1 you are multiplying with minus 2 by 3. So you require one multiplier. So therefore, one adder and one multiplier and one delay. Though we struggled very hard from the beginning to design this, but the end is very sweet. Because you can just get your design with only 3 simple arithmetic units in the digital part. How do you design analog filter, by the way? I'll give you a clue. How do you design a low pass filter? RC low pass filter.
RNC.
RNC. Is it not RC low pass filter?
Yes, sir.
And similarly, RC high pass filter. That means you need to design first resistor, then you need to design a capacitor, then inductor, then combination of them. Second order is much more complex. So you need to have 2 RC filters in cascade and then do it. Lot of problems are there in designing of this RC. That is what actually people say that the analog design is tougher than this design. Though you have taken first some kind of the approximation, finally we are done with a simple adder, multiplier and a which these 3 are easily available in any FPGA. Okay, so you take an FPGA, all these things are easily available. So you just have to write down the Verilog code or whatever it is, and then dump it and then you can. Okay. Right. So this is normally what we call DF1, but similarly you have also DF2 technique, wherein you reduce the number of adders as well as the delay. So, if you have any questions, I am ready to take. It continues because I just stopped it because I have to. Otherwise, as I said, it's a very long process. Any questions? Online, offline?
Since emissive filter will be more complexity with the development while designing. So because of getting better, means minimizing error only, we are moving for emissive filter design.
Sure.
That is only the part we are going for it.
If you require the better approximations and if you are moving towards the perfection, your design must be complex. Maybe not the right platform to give an example, but what I personally feel or what my research and my understanding is that the Apple designs are very complex. You look at any Apple product, which is the most complex design they follow, but the end user will enjoy it. That's the reason the phones are so costly also. Okay. Any other questions? No questions?
No, sir.
Right. So, thank you very much for your kind attention.